This conference will now be recorded.
Hello everyone, we last day ended at this slide. So Dalton's atomic theory, all the postulates we have seen, and also from this picture you can understand the difference between Dalton's atomic theory, which is very old theory, and the modern atomic model. In modern atomic model, the main difference is, according to Dalton, it is said that this atom is indivisible, okay? But actually atom is not indivisible. Fine, because these are the electrons that are actually involved when there is any reaction occurring. So because of this, we cannot say that Dalton's atomic theory it is there is no error. So there is also some limitations. So now one by one we will see the limitations. In the light of current state of knowledge in the field of chemistry, now the theory, there will be some limitations. So discovery of subatomic particles disproved this postulate because according to this, it says that atoms are indivisible, but actually atoms are not indivisible. Okay, so this is the difference. Now the second point, as per Dalton's atomic theory, all atoms of an element have identical masses and densities. But that is also not always true. Though we can say that mostly it is true, but it is not always true. Okay, so when it is not true, when it is isotopes, that means just take water molecule, we know the formula is H2. But another molecule that is also water, but now hydrogen is replaced by its isotope, which is deuterium. So when isotopes of elements are involved, then we cannot say that this postulate is correct, because according to this postulate it is saying all atoms of an element have identical masses and densities, but we know that hydrogen, when we consider mass, and when it is deuterium, the mass is doubled, it is not same. So in case of isotopes, this the limitation. The third point, it is possible for two different elements to share the same number, mass number. Okay, now mass number is basically, what is the meaning of mass number? It is basically summation of proton and neutron. So mass number, it will be proton number plus total neutron number, then only it is mass number. Now it may be that for two different element, this p plus n value is same. Okay, individually proton and neutron number not same, but when you are adding it, this summation is same for two different elements. It may happen, and when it is happening, then we say these two are related to by the term isobar. So the definition of isotope is same atomic number, right? But in this case, the definition is mass number is same. So you can see we have taken two elements. One is argon, another one is calcium. Argon is having mass 40. Calcium is also having mass 40. So it means for these two elements, total number of protons plus total number of neutrons, it is same. Okay, so that is the definition of isobar. When mass number for two elements same, they will be called as isobar. But according to Dalton's atomic theory, there it is mentioned that the masses of atoms of two different elements must differ, but that is not always true. Okay, next point, elements need not combine in simple whole number ratios to form compounds, but according to this theory, it is mentioned they are always combining with each other in whole number ratio, but that may not be true always. When it is not true, you will see in certain complex organic compounds. For example, here we have taken sugar or sucrose, which is having very complex large structure, but if you look at the molecular formula, here carbon, hydrogen and oxygen, if we take the ratio, okay, so it will be 12 is to 20 is to 11. Now this number you cannot simplify it further, right? That is, if you are dividing 12 by 2, it will be 6. 22 by 2, it will be 11, but you cannot divide 11 by 2 because it will be fraction. So that is why here the simple ratio, it's the maximum simple ratio that you can get for these three atoms, 12, 22, 11. So that is why they are not featuring simple ratio of constituent atoms, which is another limitation. Fine. And the last point, the differences in the properties of diamond and graphite. Now, diamond and graphite both are actually carbon. We know one element is carbon, but diamond and graphite, these two are different physical form of the same element. So if we say what is the definition of allotrope, diamond and graphite, these two are allotropes of carbon. There are also other allotropes of carbon. These two are the two examples, right? If you consider phosphorus, there is also different types of allotropes: red phosphorus, white phosphorus, black phosphorus. So what is the definition of allotrope? Allotrope is basically different physical form of the same element, and their chemical properties, their physical properties, that are also different, but actually they are same element. So whether you consider diamond or graphite, in both cases it is carbon, atomic number 6. So according to Dalton's theory, it is saying that the differences in the properties of, that is diamond and graphite, it should not be different, it should be same, because after all they are same element. But for allotropes, it is observed their properties, whether it is chemical, physical, it is different. Okay, so both of these diamond and graphite, they are containing carbon, but we cannot explain their difference in physical properties, in chemical properties, on the basis of Dalton's atomic theory. So that is the reason this is also another limitations of Dalton's atomic theory. Okay, so these are some of the limitations of Dalton's atomic theory. So it is not free of errors, so there is also some errors present. Okay, next we'll see. Okay, here we have a picture which is according to modern theory, because in this case you can see this is the nucleus, right? Where protons and neutrons, these two are present. Proton is here designated by red dot, and neutron, it is by gray dot. Okay, and the electrons, they are revolving around this nucleus, they are in blue color. Okay, but according to Dalton's theory, we know it is indivisible. Atom is indivisible. So these particles, subatomic particles, they should not exist, but they actually exist. Okay, so this is not correct if we say atoms are indivisible. Atomic mass. What is atomic mass? As atoms are very small, which is clear from this value, diameter is 10 to the power minus 10 meters. So you can understand from this dimension how small they are. Okay, and their weight, whatever is the element, because depending on element there will be different atoms, but whatever is the element, their weight, it is more or less around this value, that is 10 to the power minus 27 kg. Now as it is a very small number, even if you express it in gram, it will be maximum 10 to the power minus 24. Just multiply with 1000, it will be 10 to the power minus 24, but still it is a very small number, right? So it is difficult to measure their mass directly, and in day-to-day life, that is handling these small numbers is difficult. Hence it is proposed to have relative scale based on a standard atom. So we have to choose some particular atom which we will call standard atom, and based on that atom we will try to see the atom for which you want to know the mass compared to carbon atom, that is, it is comparative value. Okay, so that is why it is relative scale. Now for that, here we have chosen carbon 12 atom, that is mass will be 12, because carbon has different types of it may have mass 12, 14, but we will choose carbon 12, not any other carbon, because that is the most abundant in nature. So carbon 12 atom is considered as standard, that is according to IUPAC convention. and its mass is fixed at 12 AMU or unified mass. So AMU full form is atomic mass unit, or you can also express it with a simple small letter U, which is unified mass. Now we have to know what is the definition of atomic mass unit or U. So AMU or U, this mass is defined as 1/12 of the mass of carbon atom. 1/12 of the mass of carbon atom in its ground state. Now it is calculated already that this 1/12 value of the mass of carbon 12, it is actually this value 1.6605 into 10 to the power minus 27. Okay, so this is the value of 1 AMU or 1 U. Correct. Now here we have some more detailed explanation. 1 AMU, 1/12 of the mass of carbon atom. Now mass of carbon atom is 12 if we say it is in terms of gram. Okay. Now when you are dividing it by Avogadro number, because in last class we know the concept of Avogadro number. So these numbers, as we consider 12 gram, that is the mass of 1 mole. Okay, and in 1 mole, these are the number of particles present. In this case, the particle is atom. So that is why mass of 1 mole, it is 12 gram. And now we are dividing this mass by Avogadro number so that we can get the mass of 1 carbon atom. So this part, so this total quantity, that is this 12 divided by 6.023 10 to the power 23, this total quantity is basically the mass of 1 carbon atom. And there is 1/12 we are multiplying, that means it is 1/12 fraction of the mass of 1 carbon atom, and that is having this value. Okay, so if you first, that is if you divide 12 by, actually this 12 will be cancelled, and if you take the, that is inverse of 6.02 10 to the power 23, it will be in gram unit, but if you convert it to kg, you will get this value 1.66 10 to the power minus 27. If you want to express it in terms of gram, it will be 1.66 into 10 to the power 24 gram. Okay, so since 1 mole of carbon atom have a mass of 12 gram, and we know 1 mole of atoms, it contains this number of atoms. So that is why we are dividing first 12 by this Avogadro number, and then we have to take the 1/12 value of this. Okay, in this way you can get the relationship between mass in terms of kg or gram and mass in terms of AMU. So in this way, just using these values, that is 1.66 10 to the power minus 27, whether if it is kg, and if it is gram, then minus 24. So now you know if 1 AMU is that is 1 AMU is equivalent to this mass. That means if it is 10 AMU or 15 AMU, simply multiply 15 or 10 with this 1.66 value. Okay. Now if you simply consider this particular problem, your idea will be more clear. Suppose it is asked that how many AMU are present in 27 gram of mercury. That is the question. Okay, we know what is 1 AMU, right? So if we know the 1 AMU, then which is basically this mass, but our mass is given 27 gram. So if you want to know how many AMUs are present, you have to multiply with this value. Sorry, it will be kg, because it is minus 27 given. If it is minus 24, it will be gram. Okay, so in this way we can convert AMU to mass in gram or vice versa. Now atomic mass, sometimes it is also expressed as relative atomic mass, because after all it is relative scale. So if you want to express it that way, though mostly we simply say atomic mass, but actually it is relative, right? So relative atomic mass of an element, that is actually average mass of one atom of the element. Now this is something you are seeing new here, because we have not used this term before, average mass. Now why it is used, we will also discuss it in the next slide. Right now just see what is the expression. Average mass of one atom of the element divided by, that is the element for which you want to find relative atomic mass, divided by 1 by 12 of the mass of one carbon dual atom. Okay, or you can say another way, relative atomic mass, that is average mass of the atom of any element for which you want to find out the relative atomic mass, divided by unified atomic mass, which is another way of saying the same thing that you have seen in this case. So whether you say 1 by 12 into mass of one carbon 12 or unified atomic mass, it is actually same. So one example you can see here, relative atomic mass for hydrogen. If you want to calculate in terms of mu, then what we will do? First, we will take average mass of hydrogen atom in kg. You can also do it in gram, divided by unified atomic mass. And unified atomic mass is having this value. If you have done it in the numerator in gram, obviously you have to take then minus 24, not 27. So be very careful whether it is in gram or kg. So kg by kg, there will be, that is this term will be cancelled. Fine. So mostly there is no unit, but average mass of hydrogen atom in kg. And if you consider this unified atomic mass, that is this denominator, you can also write it as if it is kg per u. So if you are expressing it in that way, suppose kg per u, then you can write it u. But if you are simply writing kg and kg also in denominator, it will be cancelled and there will be no unit. So 1.008, that is actually the relative atomic mass of hydrogen. Okay. Now the question that why we are using this average mass, that answer we will get now. It is because of presence of different types of isotopes. For every element, most of the elements, they are having more than one isotope. So when there are different types of isotope, you have to consider all of them and also their corresponding abundance, and then you have to take the average value. So in the next slide you will see how to do that, how to find out average atomic mass. Since most of the elements consist of isotopes, oxygen, there is different isotope, chlorine different isotope, nitrogen different isotope. So they differ in mass, but their atomic number is same. So then we have to use average atomic mass. Now average atomic mass, if you want to define it, it is defined as average atomic mass, average of the atomic masses of all the atoms in their naturally occurring isotopes in a naturally occurring sample. So if you have taken any sample, suppose you have taken any sample of magnesium, naturally occurring sample. Now in this case, total 3 types of isotopes are present. Okay, suppose the first isotope, its mass is 23.985, and this is having the maximum abundance almost around 80%. Okay, then the second isotope mass is, actually we will see the masses are very close to each other, but still they are not same. This little difference also you have to consider. Second isotope, now it is slightly greater, 24.986, but now the abundance is 10% only. Third isotope, this is even higher, very little amount, but still it is higher, 25.982, and abundance is 11. Now if you want to know the average atomic mass, what you have to do? You have to multiply this mass with the corresponding percentage. So here we have taken 0.7899. You can also do it another way. Suppose you are multiplying 23.985 with 78.9. That is, if you are not dividing 78.9 by 100, then you have to directly take 78.99, and also for the other 2 isotopes, and then together you have to divide by 100. But you cannot avoid that. Directly you can multiply 23.985 as if the 78.99 . if you divide it by 100, it will be 0.7899. So that value is actually written here. Similarly, if you divide 10 with 100, it will be 0.1. Then it is written like this. This is also divided by 100. But you can also do it together. That is up to you in which way you want to do your calculation. But finally, the average value that you are getting, this is 24.31 AMU. Okay. So another example also we'll see. So this is for magnesium. Next we'll see for oxygen. Here we have total 3 isotopes, 16, 17 and 18. So these are the different masses, because the definition of isotope, it says atomic number is same but mass will be different. Sometimes we also express it like this. Suppose I am writing 3 oxygen and mass is 16 but atomic number 8. Then mass is 17, atomic number 8. Mass is 18, atomic number 8. So see, atomic number same but mass is different, and it is because of different number of neutron, because we know mass is P plus N. P is same, mass is different, that means N must be different. So these are the isotopes and the corresponding abundance given. It is, see, it is very high. So this is the maximum abundance. We know oxygen 16, that is the that is higher abundance. We do not use 17 and 18 much. Then the next one, which is having mass slightly higher, 18, which is even higher, but their abundances are very low. So in this case, what we will do, we will multiply all these masses with the corresponding abundance and then divide it by 100. Okay. So see, this is for the isotope 1, isotope 2, isotope 3, and then we are dividing it by 100. In the previous calculation, we have done it individually, but that doesn't matter. You can also do it together. But ultimately, what you are getting, 15.98, which is almost close to 60. Okay. So in this way, you can calculate average atomic mass. Average molar mass of chlorine, that is given 35.5 gram per mole. Remember, in the previous calculation, we have calculated average atomic mass, molar mass, but in this case, it is already given. Okay, though the units are different. In the previous case, you have seen the unit, it is in AMU, right? Just see here, it is in AMU. In the next one, no units are given, but in magnesium, it is in AMU, but it may be also in terms of gram per mole. But actually, it doesn't matter. The values are actually same. The numerical value is same. So when you say atomic mass, it is actually the unit that you have to use, AMU, that is for one particular atom. But when it is 1 mole of atom, then it will be in terms of gram per mole. So molar mass, just you have to be careful when it is mentioned molar mass, then unit will be different, numerical value is same. See, if I am saying that average atomic mass of chlorine in terms of AMU unit, that is also 35.5, but unit is different. So in this case, as we have taken average molar mass, see here it is written in the topic average atomic mass, right? But now we are saying average molar mass. Remember, it is just the difference in unit. When it is AMU, basically you are considering one particular atom. But when you are considering average molar mass, you are considering 1 mole of that particular atom. That means 6.023 10 to the 23 numbers of atom. So now the unit is different, but numerical value is same. Okay, so come to the question. It is saying that average molar mass of chlorine 35.5. Now, 2 isotopes of chlorine are there. One is 35 mass, another one is 37. So for these 2 isotopes, we have to find the ratio of 35 chlorine to 37 chlorine in naturally occurring chlorine. Different ratios are given in options 1, 2, 3, 4. So now the average value is given and you have to find their abundance. In the previous 2 calculations, abundance is given and you calculated what? You have calculated average atomic mass, but now average value is given and we have to do the reverse process. Now you have to find the abundance of 35 chlorine and 37, and after once you know the abundance, then you have to take the ratio. Okay, so this is the calculation. Now this side the value we already know, and suppose the abundance, because only two isotopes are there, so if 35 mass, that is the first isotope, if its abundance is X, obviously for the second isotope it will be 100 minus X. So that is why what we have done, 35 multiplied by X plus 37 multiplied by 100 minus X, and then together you have to divide it by 100. If you do this calculation, finally you will see the value of X is 75. That means the second isotope, it must be 100 minus X, that is 100 minus 75, which is 25. Now you have to take the ratio of 35 chlorine divided by 37 chlorine. So 35 chlorine, it is 75. So 75 divided by 25, it will be 3:1. So this should be the correct answer. Okay. Next one is also this average atomic mass related problem. Here the masses are given. Masses of all the three isotopes are given along with their abundance. See, 200x. Which element, that we do not know, that is not required also, but their masses are given: 200x 90%, 199x 8%, 202x 2%. The weighted average atomic mass of the element is closest to. Now see, their average atomic mass is mentioned, and look at the unit U. It is not gram per mole. Okay. So now the same type of calculation that we have done in the previous slide, that is 200 multiplied by 90, then 199 multiplied by 8, then 202 multiplied by 2. So you are getting 199.96, but directly this value you are not getting in any of the options. And don't choose this one, because if you round it off 199.96, it will be 200. So that is why you have to choose the last value, option D. Molecular mass. So until now we have seen atomic mass, which is mass of atom. Now we are seeing molecular mass. So all these examples that we have calculated, the examples that you have seen, it is actually containing we have considered only atom, but it is not necessary it will be atom. Suppose you have any compound, or it may be any diatomic, tetraatomic molecule. Suppose P4, phosphorus, it is tetraatomic. So 4 atoms together is making the molecule P4. So it is not atom, it is molecule. Fine. Similarly, if you take glucose, so carbon, hydrogen, oxygen, 3 different types of atoms are present. And when you combine the masses of all these 3 elements, then you get the molecular mass. So molecular mass, it will be applicable for molecule. Atomic mass for atom, molecular mass for molecule. So molecular mass is the sum of atomic masses of the elements present in a molecule. It is obtained by multiplying the atomic mass of each element by number of its atoms. So suppose I am saying 2 elements are present, X and Y. So X and Y present, and X is present total A, and this is B. So in this case you have to multiply the atomic mass of X with A and atomic mass of Y with B, because B number of Y atom is present, A number of X atoms are present. So that is why you have to do this calculation and then add it. In this way you can get molecular mass. So for that we have to know the atomic masses of all the elements, or relative atomic mass. You know now how to find it out. So here we have this table. Some common elements are mentioned and the relative atomic mass, that is also there. So now we will see this example: glucose C6H12O6, carbon number total 6. So that is why 6 into 12, See, here we have to choose hydrogen, carbon, oxygen. So 1.008 into 12 and 6 into 16. So if you add all this, you will get the molecular mass 180.096, which is approximately equal to 180. Okay. One more example. Calculate the molecular mass of ammonium sulfate. So first, obviously, you have to know the formula. If formula is given, it's fine. But if it is not given, you have to know the formula. NH4 whole 2 SO4. So in this case, first you have to, that is, you can also write it for your convenience. You can write it in this way, that total number of nitrogen is 2, total number of hydrogen is 8, total number of sulfur is only 1, and oxygen 4. So you can do it in this way, or directly you can add the masses like this. So here see, as there are 2 ammonium ion, so 14 into 1, this is for nitrogen, 4 into 1, this is for hydrogen. So for 1 NH4 unit, it is 14 plus 4, that means 18. So 18, that should be multiplied by 2, because ammonium ion is coming 2 times. Then sulfur 32 atomic mass. Sulfur is given here, yes. Nitrogen is given 14, and for oxygen it is 16 into 4, because 4 oxygen atoms are there. So finally what you will get the value, which is 132 AMU. Okay. So in this way we can calculate molecular mass. Molar mass. So though you have already seen how we have used it in one problem, remember the chlorine related problem, there we have already used this molar mass, but now we will discuss it in detail. So obviously it is now mass of 1 mole of a substance, and mostly it is expressed in terms of gram, hardly in terms of kg, mostly it is in terms of gram. So you will see it is having same numerical value, just like a, that is when you use AMU unit, only the unit is different, because now it is mass of 1 mole, not one particular atom or molecule. So that is why it is known as molar mass. Molar mass of an atom is, you can also express it like this, gram atomic mass. Okay, gram atomic mass when it is a single atom, and if it is monoatomic, suppose argon, which is noble gas, it is monoatomic. So in this case you can directly use gram atomic mass. Or if it is molar mass of an atom, that is if it is not monoatomic atom, suppose it is diatomic like oxygen, nitrogen, or triatomic like ozone, O3, then you can use gram molecular mass, because in that case if I am writing O3, you have to consider the that is atomic mass 3 of 3 oxygen atoms together. So now it is mass of a molecule. So that is why now the term is changed from gram atomic mass to gram molecular mass, because it is not no longer atom, now it is molecule. Okay, though all are same atoms, but it is a molecule. Similarly, if it is any compound where 2 or 3 elements are present, just like glucose, then also you can say molar mass or gram molecular mass. 1 mole of a substance has the same mass, that is numerical value is same in terms of gram, and when it is one atom or molecule in terms of AMU unit. So just units are different, numerical value is same, and the difference is when it is AMU unit, it is a single atom or molecule you are considering, but when it is in gram, now you are considering Avogadro number of atoms or molecules. That is the difference. That is why the unit is changed. The numbers in the periodic table that you see, that we identified as the atomic masses of the atoms. So you will see, if you look at periodic table, these some mass values are given. So these mass values, it may be, it just as numerical value is same, whether you use AMU unit or gram per mole unit, whatever unit you use, in both cases as it is same numerical value, So from this value which is mentioned in the periodic table, it not only tells us the mass of one atom in terms of mu or u, but also tells us the mass of 1 mole of atoms, of 1 mole of molecule also you can say, in terms of gram. Okay, the molar mass in terms of gram, it is numerically equal to atomic mass, molecular mass, or formula mass, depending on whether what you are actually considering. Okay, so this is the difference between molar mass and atomic mass. Now if we solve some problem, the idea will be more clear. It is asking that how many moles of NaOH present in sample which is 200 gram of NaOH. We know what is the mass of 1 mole of NaOH. That is, we know what is the molar mass. How? You have already seen in the last slide how we have calculated the molar mass of C2H12O6 glucose, how we have calculated the molar mass of ammonium sulfate. So same thing you have to do here. Okay. So the mass of 1 mole of NaOH, simply just add 23 which is for sodium atomic mass, 16 which is for oxygen, 1 for hydrogen. So if you add these three, you will get 40 gram. So this is for mass for 1 mole. That is why the unit is gram. So if 1 mole is having mass 40, but sample is 200 gram. So simply when you divide it by 40, you will get the total number of moles, which is 5. Another example. Calculate the mass of an atom of oxygen element. Now it is not mole. We want to know what is the mass of an particular atom of oxygen. But we know the mass of 1 mole of oxygen is 16 gram. And number of atoms in 1 mole of oxygen is Avogadro number, right? So we can say in another way that Avogadro number of oxygen atoms will be having this mass. So one atom will be having mass 16 divided by Avogadro number. So that is why when you divide 16 by Avogadro number, basically you get this value. Okay. So in this way we can calculate the mass of one atom of an oxygen element. Fine. Some more idea we will see about molar mass. Here we have the single water molecule, just one water molecule. Okay. So in this case, the relative molecular mass, simply you have to add 16 plus 1 plus 1. But as it is a single molecule, the unit must be in terms of AMU or simply U. Now when I am saying it is 1 mole of water, obviously it is not single molecule. See, now there is a picture of a bottle which is containing 1 mole of water. And here, if you take a small part, you will see there are some molecules of water, right? So molar mass is now mass of 1 mole, which is again same numerical value, just you have seen in the previous case, 18. But now it is gram per mole. So it is the mass of 1 mole. So that is why we are saying 18 gram mass per mole for 1 mole. Okay, that means for Avogadro number of water molecules. Here we have in these columns name of some compounds, then mass of the substances taken in gram, that is the sample mass, that is given mass. Fine. And then sorry, it is mass of the substance is basically the molar mass, you can say, because it is in terms of gram. So for elemental carbon we know it is 12 gram, for glucose we know it is 180 gram. And here in the third column it is given mass of single atom. For carbon you have to use the term atom, but when it is glucose it will be molecule. So that is, it is mentioned mass of single atom or molecule, but it is in gram unit. So these are the two values. So you know what is the mass of the 1 mole. And you also know what is the mass of single atom or single molecule. Okay. Now, if you divide 12 by this single atom mass, which is also in gram, so 12 gram divided by this number, so obviously now you will get Avogadro number. So as if we are doing the reverse calculation. Normally what we do, we divide 12 by Avogadro number, then you get mass of single atom. But reverse also is possible. 12 is the mass of Avogadro number of particles, atoms or molecule, whatever. 12 is actually for atom, 180 the mass of Avogadro number of glucose molecules. And this is for single. So if you divide it, obviously you will get the Avogadro number. Okay, which is, you can say, the number of atoms or molecules present in this particular amount, and this particular amount is nothing but molar mass, right? Similar type of example, now it is for potassium dichromate. K2Cr2O7 is the formula, potassium permanganate, KMnO4 is the formula. If you consider all of its atomic mass in terms of gram, 2 potassium, 2 chromium, 7 oxygen, you will get this value. So this is the molar mass, and this is also the molar mass of KMnO4. 3 elements are there: potassium, manganese, oxygen. And these are the masses for a single molecule. So if you divide it, you will always get Avogadro number. Okay. So these are that is their relationship. You can divide molar mass by Avogadro number. In that case, you will get the mass of one particular molecule or one atom. Or if you are doing the reverse, that is, you are dividing now molar mass with the mass of single atom or molecule, now you will get Avogadro number. So related problem. Hemoglobin contains, we know hemoglobin contains iron, but it contains 0.34% of iron in terms of mass. Now the number of iron atoms present in 3.3 gram of hemoglobin, that we have to find. Some informations are given. Atomic mass of iron is given 56 U, and Avogadro number, though mostly we can remember this value, it is used so many times, so frequently. If you can remember it, it is better, because sometimes in problem it will be given, then it's fine. So percentage of iron is given, and the sample mass of hemoglobin, given mass of hemoglobin, that is also given. So from this information, you have to find how many iron atoms are present in this sample of hemoglobin. Fine. 4 different options are there. Obviously, as it is number of atoms, atoms, it is numbers are very high value. So first see, as we know the percentage, so 0.34 amount that is present in 100, because it is percentage. So if you multiply this with 3.3 divided by 100, you can get the mass of iron, that is total mass of iron that is present in this given sample. Okay. Next step is, now you have to find the number of moles of iron, present in this amount of iron. Okay. So we know that atomic mass is 56 U, and though it is in U given, but you can consider it is in gram. So you are dividing 0.01122 divided by 56 gram. So gram is cancelled because numerical value is same. Okay? Don't bother about that. So GG cancelled, and you can get the total number of moles. But remember, it is number of moles, it is not number of atoms. You have to find number of atoms, right? So once you know the number of moles, by dividing this mass 0.01122 by the gram atomic mass of iron, I'm saying gram atomic mass because it is having unit G. So now you know the number of moles. Once you know the number of moles, you can easily convert it to number of atoms. and for that you have to multiply it with Avogadro number. So number of atoms, iron atoms present in these moles, simply multiply with Avogadro number, because for 1 mole the number of atoms is Avogadro number. So for 2.10 to the power minus 4 moles, it will be multiplied by Avogadro number. So finally what you are getting, 12.044 10 to the power 19. If you convert it to scientific notation, which is, remember, the value is less than 10 but greater than 1. So if you express it in terms of 1.2, so you are shifting the decimal, so that is why now the power of 10 will be 20, and this is matching with option C. Okay, directly you cannot compare, though it is closely matching with option B, but remember power is not matching, so it cannot be correct. So after shifting the decimal towards left hand side, now the power is changed from 19 to 20. It is matching with option C. Okay. Five moles of a compound AB2. That means one of that A element, two B element, two atoms of B, one atom of A. It is having mass 125, 10 to the power minus 3 kg, and 10 moles of another compound of the same elements, but now formula is different, A2B2. We have taken 10 moles of it and the mass is given 310 power minus 3 kg. You can also consider it gram, then it will be 300 gram, right? The molar mass of A, which is Ma, molar mass of B, which is Mb, you have to find in terms of the unit kg per mole, not gram per mole, kg per mole. Be very careful about the units. Okay, so different options are given. So as it is Ma and Mb, these two are the molar masses, and that are unknown. We have to find this unknown value. But from the formula AB2, you can write that Ma plus 2Mb. Okay, Ma plus 2Mb, that should be equal to this, because when it is Ma plus 2Mb, it is for one formula, that is 1 mole AB2. So for 5 moles, it is 125 10 to the power minus 3. So for 1 mole, it will be 125 divided by 5, which is 25 into 10 to the power minus 3. And molar mass of AB2 and A2B2, this should be like this. 2 times Ma plus Mb for the second formula, first formula Ma plus 2Mb. But for 5 moles, it is 125. For 1 mole, it will be divided by 5. So it is 25. Similarly, for the second one, 300 must be divided by 10. So now it is 30 kg. So when you will solve these two equations, I will suggest when you are solving, just remove this 10 to the power minus 3, because it doesn't matter, as if you are converting it to gram. So Ma plus 2Mb equal to 25 gram. You can also write like this. Ma plus 2Mb, you can also write 25 gram. Okay, and for the second one, you can write 2 Ma plus Mb equal to 30 gram. So calculation will be easier. You don't have to handle with this power term. If you solve this in this way, you will see that Ma is equal to 5 gram, Mb is equal to 10 gram. But as it is mentioned, you have to finally express it in terms of kg per mole. So once you have already solved Ma, Mb, now just multiply 10 to the power minus 3. That's it. That you have to do. But while you are doing the actual calculation, just avoid this term. So in this way, it will be easier for you. So it is matching with option 3, right? 5 into 10 to the power minus 3, 10 into 10 to the power minus 3. Other options, if you see, it is reverse, right? The first option. Second option, obviously, it is not correct. The third option is also just like option 2, but in reverse order. So option 3 is the correct option. molar volume. The volume occupied by 1 mole of any substance. Obviously, from the term you can understand it will be volume of 1 mole. Just we use the term molar mass. It means mass of 1 mole. So when it is molar volume, it will be volume of 1 mole. Okay. And we have already seen in Avogadro's law that when temperature and pressure it is fixed, then whatever is the gas you have taken, oxygen, nitrogen, hydrogen, anything, if it is same number of moles, volume will also be same. So volume occupied by 1 mole of any substance in gaseous state at a given temperature and pressure, that will be called molar volume or gram molecular volume, but mostly we use the term molar volume. And it is only applicable for gases, because when we are saying volume, obviously it is applicable for gases, right? So normal volume, that is indicated by V. This is the unit dm cube. Mole, mostly we use small n. And molar volume, now it is again V with a subscript small n. So molar volume, now look at the unit, it is dm cube per mole. So here we have total 3 terms, and in the right hand side you can see how they are related to each other. So when it is volume, it basically equal to number of moles multiplied by molar volume. Similarly, if it is n, now it is volume divided by molar volume. These two sign is there, V by Vm. When it is molar volume, now it is V by m. V by Vm. And the first one is simply multiplication. So in this way, these 3 terms are related to each other. Now in problem, maybe 2 of them will be given. Obviously, you can now find the third one. Now in this picture, you will be able to understand the relative relationship. So this mole term is very important, right? Because once you know mole, it is related to so many other terms. It has relation. So that is why if you know mole, and when you are multiplying it by molar mass, you can get the amount of a substance in gram unit. Similarly, see the arrow is moving from mole towards this. But when you are your purpose is to convert amount of a substance given in gram to mole, so now the direction is towards mole. Now you have to divide it by molar mass. Okay. Now come to the right hand side. Mole is given, you want to get number of total entities, whether it is atoms, molecules, electron, proton, whatever. So I am saying suppose x moles of electron. So what you will do, now you will divide that x mole with Avogadro number so that you can get the total number of electron entities. Similarly, when entities are given, you want to know how many number of moles. Now you have to divide it by Avogadro number. Fine. Now come to the lower part. Suppose mole numbers are given, you want to know the volume of the gas. Suppose the substance involved, it is gas. You want to find out mole volume in terms of liter at STP. Now this relation is applicable only at STP. So if you multiply the number of moles with 12.4 liter under STP condition, you can get the volume of any gas in liter. If volume of gas in liter is given under STP condition, then if you want to calculate number of moles of that gases is present actually, you have to divide this volume in terms of liter at STP by 22.4. So in this way you can understand how this mole term is related. It is 12.24 liter, or you can say 22400 ml. Okay, so this relationship it will be very helpful for you, because when you will solve different types of problem, because from this single picture you can get the idea how to convert from mole to number of entities in the right hand side, from mole to volume of gas, but it has to be under STP condition, from moles to the amount of the substance in gram, that is a given sample. or in reverse way, if amount of any substance is given by the help of molar mass. Obviously you should know the molar mass, otherwise how many moles are present, that you cannot calculate. So to convert amount of mole to amount of, sorry, number of moles, not amount of mole. So to convert this to this or this to this, you obviously you have to know molar mass. Similarly, when you want to convert mole to number of entities or vice versa, you have need this Avogadro number. And when you want to convert mole to volume or the reverse, you have to know these five. Okay, these are the conversion factors by which you can convert mole to other quantities. Okay, so we will end here. Next class we will discuss some related question, so your idea will be more clear. We are ending here. Thank you for listening.